it is trickling filter, bio tower, and rotating biological contactor. So we will cover in detail on trickling filter and also bio tower, and just a short introduction on rotating biological contactor. Okay, this is suspended growth process. If you have never seen it, what you can see on the screen, suspended material or suspended solids, these are our microorganisms. Okay, about 80% of them are our microorganisms. There are so many of them that we can see them with our naked eyes. Okay, when we learn water treatment, we count our microorganism, how many of them per 100 milliliter of water, for example. But in biological process, their number is so large that it is not realistic to count them. Instead, we measure them in terms of concentration of suspended solid in milligram per liter. So this is the suspended growth of the activated sludge process last time. So compared to, this is the media, one of the type of media that we provided, and as you can see, there is growth on top of the surface. So these are the microbes. They form film on top of the surface of the media. So theoretically, in attached growth process, we have filter media. Okay, this is the filter media, many kind of filter media which we will discuss later on. And what we will do, we will pass our wastewater on the surface of this filter media. Okay, the wastewater will pass through this filter media, and with time, microorganism growing on the surface of this filter media. Okay, with time, initially it will be thin, and then it become thicker and become thicker and become thicker. However, the maximum thickness that we will find is maybe around a few millimeters. Okay, few millimeters. So it is not that thick, it is very thin actually. But because the size of the microorganism is very small, which is about the size of the bacteria, for example, only 0.5 micron meter. The size of the bacteria is only 0.5 micron meter. So one meter is considered big for them. Okay, 1 meter is considered big for them. So this is 0.5 millimeter and 1 meter, micron meter. So you can imagine how big is this biofilm from the point of view of the microorganism. So as the film grows, okay, it will grow and grow, and this is the that pass through the wastewater that pass through the biofilm. Initially it pass through the media, and eventually the microbiofilm will develop. So as we pass through the wastewater, because in the wastewater there is food, so the nutrient and the food from the wastewater will be absorbed into the biofilm. Okay, as the same goes with the oxygen. The oxygen will also be absorbed by the biofilm, and with that the biofilm will grow. But eventually, when the biofilm get relatively thick, okay, from the point of view of the microorganism, we will find that the inner part of the biofilm will become anaerobic. Okay, because the microorganism at the surface of the biofilm will consume the oxygen. The oxygen will penetrate the biofilm, and as it penetrates the biofilm, it will be consumed by the microorganism that live on the surface or at the outer side of this biofilm. So as the gas pass through into the inner side, there will be less oxygen and eventually no more oxygen. So now later on, this part of the biofilm will become anaerobic, and the outer part will become aerobic. So the food that is available from the wastewater will be absorbed into the biofilm, consumed by the outer region of this biofilm, of the microorganism. So as it gets thick, very little food will be available for those biofilm at the inner side, and eventually there will be no more food for them. So what happened next is that once there is no more food, and what happened is that the microorganism that live in the inner side will eventually die. And when they die, okay, if this part of the biofilm, when the microorganism die or majority of them die, so there will be no more microorganism that hold the biofilm on the surface of the media. So eventually, this portion of biofilm will be peel off or will drop from the biofilm because no microorganism is holding the biofilm on the media. So this portion of the biofilm will peel off from the media and it will go with the wastewater into the next stage. And the new biofilm will grow. So this will happen continuously throughout the media. Okay, this is something that the common phenomena that will happen throughout the life of this process, and you will see the biofilm leaving the media, and you will see also the new biofilm being formed on the surface of the media. Okay, so I repeat again. So the concept is that media, the biofilm with availability of food and also oxygen will grow on the surface of the media. Food and oxygen will be absorbed, but eventually as they get thicker and thicker, only the outer part will receive the food and the oxygen. The inner part will become anaerobic, and there will be no more food available for the microorganism in the inner side of the biofilm. And eventually those in the inner side will die, and they will no longer hold the biofilm on the media. So that patch of biofilm will fall off from the media. And this process will continue continuously at different places. New biofilm will be formed, old biofilm will fall off, and again and again. Any question? Any question? No? So this is a very important concept for you to understand. Okay, Najib, what's your question? Okay, Najib asked, when the biofilm fall off, does it mix with the wastewater? Yes. When this wastewater, it will flow from, for example, from top to the bottom. So the falling of the biofilm will be carried away by the wastewater, and it will be brought to the next process, which is the secondary clarifier. Okay, so again, Najib and the rest. So when the biofilm fall off from the filter media, it will be carried out by the wastewater, and it will go to the next process, which is the secondary sedimentation or secondary clarifier, which we will see later on in the flow diagram. Okay, I hope I answered the question. All right. Any other question on this? This is one of the favorite questions that we would like to ask students on their understanding of this process. Okay, on the understanding of how the attached growth process work in treating wastewater. So you must make sure that you understand the process. You can even draw this diagram again. I mentioned just now there are three example of trickling of the process, which is trickling filter, biotower, and rotating biological contactor, or we call it RBC. So now I'm going to discuss on trickling filter and eventually biotower. Okay, trickling filter is a very old process. It started in the late 80s, in the late 19th century, 1880 something. It was first established in England, and then later on become popular in other parts of the world, and it is more developed later on, and now some of it are also being used in Malaysia. However, it is not that popular in Malaysia as compared to activated sludge process, but we do have some of it at uh, relatively old system, but one but not commonly used in Malaysia. Okay, this is the diagram of trickling filter. It comprises of three components. One is the distributor, arm distributor. So this arm distributor will rotate. I will discuss this in detail later. This is the filter media. This is the media where the microorganism will form the biofilm. And the filter media is supported by, by the under drain system. Okay, the gray one. So this is the under drain system. So there are three components for this trickling filter, and also bio tower, which is the distributor, the media, and also the under drain. Will come from the middle. It will be pumped upward, and then the rotator or the distributor will rotate to distribute the wastewater along the surface of the filter media. Okay, the wastewater will come from the bottom, go into the distributor arms, and the distributor arm will rotate, not using motor actually. It will rotate because of jet the wastewater coming out from the distributor. So because of the hydraulic jet produced by the wastewater coming out from the distributor, it will rotate by itself. And there is a ventilation port, if you can see down here. Okay, this is for better oxygen flow or airflow within the filter media. If the filter media does not have good oxygen or airflow within it, it will become anaerobic, and it will not be good for the system. It will make the system smelly, and it will not. It will cause poor performance of the system. So that is why we need a ventilation port, and the air will pass through the pore of the filter media, or the opening of the filter media. Okay, this is the rotary distributor. You can see here. So this is the media. Okay, so the wastewater come out from the distributor like this. Okay, so you can see there is a hydraulic jet being produced by the wastewater on four arm. Okay, this is four arm distributor, and it is either four arm distributor or two arm distributor. So because of this, it will rotate. It is very important during the maintenance of this uh, trickling filter that there is no what there's no solid that will choke the opening of the distributor. Otherwise, then it will not get a good flow, and then the wastewater will not be treated properly. So this is how the wastewater will go out from the distributor. So as it rotates, the whole surface of the media will be wetted by the wastewater, and the wastewater will move downward to the bottom by gravity. So at some point, as you can see, there will be time when the microorganism or the biofilm will be exposed to the wastewater or to the food, and when there is no wastewater exposed to the biofilm, the biofilm will be exposed to the air. So that is when they will get the oxygen. So at one time they will get the food, another time they will get the oxygen from the air. And also they can also get the oxygen from the wastewater. Okay, this is the video. Structure right there. There's no electric drive coming around, no motors. It's all spinning just from the water rushing around. It's pretty amazing. At any rate, the rocks in the trip can go about 60 feet. Underneath the rocks, there is a support structure and then an open channel underneath that. So the water is going through the channel at the bottom. You can see if you look at the distribution arm there, there's a lot more water coming out the end than there is towards the surface. That's because if I took a 1 foot wide section and followed it all the way around, there's a lot more outside than there is on the inside. If I want to put the same amount of water everywhere, I have a lot lower flow towards the inside. Okay, ada beberapa perkara yang di-point outkan oleh there are few things that has been pointed out by the narrator. One is that this trickling filter is 60 foot in diameter. Okay, it is very huge, 60 foot in diameter, and as you can see, compared to the diagram or the photo that I show you just now, the media is made of stone. Media is made of stone. This one, the media is made by plastic. Okay, the media is made by plastic, and this one, the media made by stone. Okay, and it also mentioned by the narrator is that the rotator is rotating by itself without any motor. Okay, because of the hydraulic jet of the wastewater coming out from the distributor. Point that he raised is that the distribution of the hole that release the discharge the wastewater is not uniform. You will have more holes at the end of the distributor and less hole at the center, towards the center, because the area within the center is small and it get bigger as it goes to the end of the rotator. So here it need more holes so that more wastewater will come out from this side at the so that they can distribute the wastewater uniformly. If they have a uniform distributor hole, then you will have more wastewater coming out from here for a very little area, and less wastewater will be coming out towards the end, which has more area to be filled up. So that's why the distribution of the hole is that it is less at the center and it get more and more towards the end of the distributor. I hope you understand. Yeah. Okay, on the filter media, as we know, it provides a phase for the biological growth, and it also contain pore or a voice or opening for passage of liquid and air passing through the media. And this is very important because if the media does not have sufficient voids or openings, then the solids will fill up the voids and it will block the flow of the liquid and also the air. So it is very important that the media has sufficient opening or voids in order for the wastewater to pass through and in order for the air to pass through the media. So this is a very important characteristic. So for trickling filter, there's the difference between trickling filter and bio tower. We will see later on. So for trickling filter, normally they use crushed stone. Okay, stone as we saw in the video just now. And the height for the trickling filter is only about 2 meter. Okay, the height of the trickling filter is only 2 meter. So the important characteristic of the media, okay, this is a shown. This is wood, okay, but this is not that popular because this is not sustainable. After some time, it will break. So the important characteristic of the media has high surface area per unit volume, meaning that actually the smaller the media, the better. However, it should not be too small. Principally, the smaller the media, the greater the surface area and the higher the ratio of surface area per unit volume. So the smaller the better. But the smaller media that you have, you will get smaller void or smaller opening in between the media. So you have to balance between the area and also the void or opening created by the media. Okay, so for trickling filter, normally the stones are not too big and not too small. Then low in cost, of course, gravel or stone is not that expensive, high durability and also high porosity. This is the one that I mentioned on the void or the opening. Okay, and the last thing is the under drain. This is the under drain system. Okay, the under drain system. The purpose of this under drain system is to support the media and also to provide opening for the wastewater to pass through. Okay, they have drainage system here. So the wastewater will go from top to bottom and it will pass through the under drain system, which will bring the wastewater to the next process, which is secondary clarifier. Okay, and as I mentioned just now, the height of this media for trickling filter is only 2 meter. That is why, as shown in the video just now, the diameter of the trickling filter is 60 meter length, which is very, so the trickling filter is very big in terms of space requirement because the media is only 2 meter height. The reason for the media to be only 2 meter height is because if you use stone, you will require a strong wall, a stone wall. And normally, we don't want to make it such a big structure. So that's why they only limit the height of the media up to 2 meter only. That is sufficient enough. But because of only 2 meter height, it requires a very huge space. Okay, this is the component of activated slush system, which we discussed last time. You have aeration tank and clarifier. So for trickling filter, we have, okay, this is trickling filter or bio tower. This is the trickling filter part. And then you have secondary clarifier. So again, this is the last time, aeration tank, and then final clarifier. Now we have bio tower or trickling filter followed by secondary clarifier. So as you can see here, the difference is we replace the aeration tank with the trickling filter. Place the aeration tank in the activated slush and we replace it with the trickling filter. Another main difference between trickling filter and activated slush is that we have return slush for the aeration tank. Okay, but for the trickling filter, the slush is not recycled. Okay, the slush is not recycled, but there is recycling of wastewater. There is recycling of wastewater. The wastewater that pass through the media, it either being recycled back at the bottom here, as you can follow, if you can follow my laser, it is being recycled, pump back into the dosing tank, and then pump again up into the trickling filter. Or after passing through the clarifier, where all the solids has already settled, the super pattern, or the one, the clarified wastewater, some of them will be recycled back into the trickling filter. In activated sludge, we recycle the sludge. Okay, but in trickling filter or in biotower, we did not recycle the sludge, but what we recycle is the treated wastewater. Okay, so why do we have to recycle the wastewater? Anybody got any idea why do we have to recycle the wastewater? Farah, BOD, what do you mean by BOD? Okay, Najib. Okay, good. Najmi, some of you answer that to make sure the BOD elimination is maximized. Yes, that is correct. But why didn't we recycle the wastewater in activated sludge? Why here we recycle the wastewater? Why not in activated sludge? So don't we need to maximize the BOD removal in activated sludge? Any idea? Okay, this is activated sludge. As you can see here, let me move this. As we can see here, for the activated sludge, we have hydraulic retention time for this retention tank, right? The hydraulic retention time is equal to volume divided by flow rate. Whatever the size of the flow rate, untuk for the for the aeration tank, the wastewater will flow. One moment, I want to turn off my okay. Right. Okay, for this aeration tank, the wastewater will flow into the aeration tank and it will stay in the aeration tank according to the hydraulic retention time, which is equal to volume divided by Q. If you design the system in such a way that the hydraulic retention time is 4 hours, so the wastewater will stay in the aeration tank for 4 hours. One moment again. One moment. Okay, for aeration tank, the wastewater will stay in the aeration tank according to the hydraulic retention time. But for the biotower, as if you can see here, the wastewater is pumped to the top of the trickling filter of biotower and it will flow down by gravity. Can you control the hydraulic retention time of this wastewater in the trickling filter? Can you? Okay, no, you cannot. The wastewater flow through the media by gravity. So you don't have any control on the hydraulic retention time. The concept is that the higher the media, the better the contact between the wastewater and the microorganism or the biofilm. If you have 2 meter, so the contact is only within that 2 meter. But it's very difficult for you to tell the time because it depends on the gravity flow of the wastewater. So because you do not have any, you do not have any control on the retention time here. That's why you need to recycle the wastewater back into the bio tower or the trickling filter until you got satisfied BOD removal. Okay, so the purpose of this recycling of the wastewater is to ensure, as you said just now, to ensure that the BOD is sufficiently removed. And why we have in trickling filter, not in the activated sludge system, because the wastewater that pass through the trickling filter is via gravity, and we do not have any control with the hydraulic retention time of this system. That is why when you look later on in our design process, there is no calculation on the hydraulic retention time because we cannot control the hydraulic retention time. And you will see also later on, if previously in activated sludge system, the cycle sludge ratio value is normally less than 1. For this effluent recycle, it also has its R value, and the R value is normally higher than 1. Okay, to make sure that all the wastewater get recycled several times into the media in order to ensure that the BOD removal is maximized. Okay, that is the purpose why we recycle wastewater in trickling filter or biotower. I understand with the clarification. Okay, so this is the process flow diagram again from different perspective. We recycle the wastewater as I mentioned just now, or sometimes in the system they have two trickling filter working in series, working in parallel, working in series. This is from primary clarifier. It goes into the first trickling filter, and then the wastewater coming out from the first trickling filter will go into the second trickling filter. And then the wastewater from the second trickling filter, some of it will be recycled back, some of it will be will go into the sedimentation tank. Okay. There is no slash return here. This is a mistake here. There's no slash return. Okay, this is the flow diagram of trickling filter. Okay, again, I want to repeat the recycle flow. We recycle the flow in trickling filter, but not the biomass, like activated sludge. And it can be operated in series and followed by a secondary clarifier, which is a typical flow for sewage treatment plant. Advantage of this trickling filter, as you can see just now, the diameter of the trickling filter is very large. So it requires large land area. So this is not feasible in area where land is expensive. Okay, in Malaysia, urban land is expensive, so you cannot provide large land or big land for wastewater treatment. It is better to turn the land into commercial area where you can get money. But to treat wastewater is not a good investment. Large land requirement, and then there is a variations in effluent quality, so meaning that the effluent quality is not stable. Sometimes it is good, sometimes it is not good. The other problem is that you will there is odor problem and filter slice problem. What does that mean? If you can see here, this system is open. Okay, this system is open to the environment. This photo is taken, or this video is taken in the US. Okay, in the US they have temperate climate. Their temperature is not that high, so the smell is not that critical for them, and also there is not much flies in their area, but still there is problem with flies, with rodent, ticos, or any other insects. But for tropical country like Malaysia, with hot climate, lots of rain, so this large area is not good. Okay, this large area is not good. You will have odor problem. You will disturb your neighbor, and also because of this is a dirty place, and our tropical country climate encourage the grow of many type of insects, flies, mosquitoes, rodent, mouse, whatever you want to call it. So that a good housing for this organism. So that is why this system is not good in countries, especially Malaysia. Okay, so because of that, they have developed a new system of the same kind. They want to avoid this large land requirement, and they want to reduce the odor problem and also filter flies. So they introduce. Okay, before that, if anybody got any questions or you haven't punched in, please do so. So now that is when they develop a new trickling filter. They call it bio tower. And why it is called bio tower? Because the media is high, or it is basically a deep trickling filter. So just now I said the height of the trickling filter is 2 meter. So for bio tower, it can go up to 6 or 7 meter. Okay, it can goes up to 6 or 7 meter. Can it go up to 6 and 7 meter? Because of the media. Okay, we will look later on what type of media being used. So the same thing, you have the wastewater influence coming in from the middle of the media, and you still have a distributor, either hydraulic or motorized distributor, and then this is your media. Okay, so the wastewater will also flow through by gravity into the media. Still have this underdrain system, and you have a ventilation window, and optionally you can have blower at the bottom to increase the air flow in the media. Okay, so this is actually the one that I showed you just now. This is the bio tower, and you can see the media is made of plastic media. Okay, this is the type of media for trickling filter. It has big opening and different type of design to increase the surface area of the media so that more bacteria can grow on the media. So the opening is big to avoid uh, choking of the wastewater or blockage of the media, and then also for good ventilation, or air ventilation for the system. And this weight, because it is lightweight, you don't need strong structure. Just now I said that when the media is made out of stone, you will require a strong wall to hold the media, to hold the stone. But because this is plastic, you don't need that strong wall to hold the plastic media. Because of that, it can go higher, much higher, and it can go up to 6 to 7 meter. Okay. The difference between bio tower and trickling filter, the main difference is the media, the type of media. And because the bio tower use plastic media, it can go high and that is why we changed the name from trickling filter to bio tower. Okay, before that, just for clarification again, why we call it trickling filter in the first place? As you can see just now, from the wastewater trickle from the distributor. Okay, the wastewater trickle from the distributor. That is why we call it trickling. But do the media, do the stone filter the wastewater? Is there any filtration process take place like you have in sand filter in water treatment? The answer is no. There is no filtration process in trickling. But in the old days, when the system was first established, those people at that time, when they passed the wastewater through the stone, they found out that the wastewater coming out from the stone was much cleaner than before. So because that time there is no knowledge on the biological process, biofilm whatsoever, they thought that the stone was filtering the wastewater, making it clean. They call it trickling filter. Trickling filter is actually an historical name established during the old time, but it was not changed until the modern time. But we have to remember, we have to understand that in trickling filter, there is no filtration process take place. The removal is made by the microorganism that form the biofilm on the surface of the media. That is actually what happened. And the same goes with the that the media used in biotower is much lighter, and because of that it can go higher, and we call it biotower. It's like Petronas Tower because of the height. So this is biotower. It is not as high as Petronas Tower, but it is higher than trickling filter. Understand? Okay. All right. Of media based on the high surface area per unit volume, low in cost, high durability, and high porosity. So for this media, the advantage of this media, you can design your own pore size. What pore size you want, what diameter you want for the pore size, you can design it on your own. But if you use stone, the size is random. The size of the stone is random. So does the pore size of the in between the stone. It is also random. You cannot control it. The only thing that you can do is that if you want bigger pore size, bigger opening, you use bigger media. If you want smaller pore size, you use smaller media. But here, you can design the size of your opening or pore size. Okay, this is actually one of the bio tower Senai Utama in Johor Bahru area. Can you see any bio tower here? It looks like a poor design house. A big bungalow, unfortunately with very limited number of window. Because this is not a house or a bungalow. Actually, inside this building is the bio tower. Bio tower is designed inside this building to protect problem of odor and also to protect the problem of insects. But now this system is no longer being used. But this was then at that time. There are many of these in Malaysia. So at one time, the system was being accepted to treat sewage in many parts of the country. But later on, there are some problem associated with the design of the system. So they discontinued the system and changed it to activated sludge. Okay. So this color, the green and blue color, is the official color of IWK. You should know this if you are Malaysian and if you don't live in Kelantan, because Kelantan is not sewage treatment plant in Kelantan is not operated by IWK. Only recently agreement to transfer this treatment plant to IWK. Before this, it was operated by Majari Sendirian Berhad. Only in Kelantan, Pasir Gudang and Johor Bahru area are not covered by IWK. And also East Malaysia, Sabah and Sarawak. The rest of the countries are operated by IWK. Okay. This is the design of activated trickling bio tower. After this, trickling filter and bio tower has the same design process. So this is the hydraulic loading. Okay, all these are in your notes if you download it. So the hydraulic loading is equal to Q, the flow rate, divided by the surface area of the media. Okay, the hydraulic loading is equal to the flow rate of the wastewater recirculation, okay, without recirculation, divided by the cross-sectional area of the media. And you have BOD loading, which is, last time we call it mass influx, which is equal to the effluent concentration multiplied by the flow rate. And then we have this Eckenfelder formula for the design. So this equation is by Eckenfelder. So what happened actually in the United States, they have lots of trickling filter, but there is no proper design equation being used for the design of trickling filter at that time. So Eckenfelder in the 60s, he made a study on, I think, about 200 trickling filter in the US, and from the data that he collected, he come out with this equation. The equation is called Eckenfelder equation. There are some other equations being used to design the trickling filter, but the most famous one is the Eckenfelder equation or formula. So here, Le is the effluent substrate concentration. Last time we call it S, but here we call it Le. D is the depth of the media. K is the dilutability constant relating to the wastewater and the medium characteristic. So with relating to the wastewater means sometimes it can be sewage, or if industrial wastewater, then it will become different. And also depend on the type of medium that you use. Either you use plastic, stone, or whatever. For simplicity of the design, we use K equal to 0.06 per minute. N is the coefficient relating to the medium characteristic as well. Simplicity, we use 0.5 as the value. R is the ratio of the recycled flow to the influent flow. Okay, similar equation to the one that we use in activated sludge system. LA is the BOD5, the mixture of raw and recycled mixture. Okay, you have recycled wastewater and you have raw wastewater coming in. So the mixing of BOD of the raw and the recycled, LA. Okay, and LA can be calculated using this equation. Li plus, excuse me, Li plus RLE plus divided by 1 plus R. Okay, so these are the only equation that we will use in our design of trickling filter. Okay, so here this is Q, this is the QR. Okay, Q. So you know the BOD of this QR, you know the BOD of this Q, so you can calculate the LA using that equation just now. Okay, again, for those who have not punched, all right, let's look at this example. We will finish, I think, around 10 or before 10 for today. An existing 6-meter deep tower trickling filter, an existing 6-meter deep tower trickling filter plant cannot meet the effluent standard of less than 10 milligram per liter. So the effluent standard is actually 10 milligram per liter, but the plant cannot meet this standard. The plant effluent BOD is 220 milligram per liter. Primary effluent BOD is 150 milligram per liter. The plant final effluent currently is 30 milligram per liter. And the recirculation flow is 1.5 of the wastewater flow entering the plant. One proposal is to change the recirculation ratio to reduce the effluent BOD from 30 to 10 milligram per liter. The constant for the random plastic media N equal to 0.44 and K20 of 5 per minute. The design temperature is 25 degrees Celsius. Okay, there are many information that we need to capture here. One thing, the depth of the tower is 6 meter. Okay, I want to ask you, it says here the effluent BOD is 220 milligram per liter. The primary effluent BOD is 150 milligram per liter. So what LI should we use in our design? The value of our LI. 220 or 150? Okay, what is the value of our BOD influence, LI, coming into the 150 or 220? I got different answer. At some 150, 220, 150. This is influence. This is primary clarifier. After primary clarifier, it goes into our trickling filter or bio tower. So what is our LI? This is 220, 150. So the answer should be LI is the one coming into the trickling filter. This is coming to the primary clarifier 220. So the primary clarifier is some of the suspended solid. So the BOD become 150. And then it goes into the so the LI influence substrate coming into, it should be 150. Okay, it should be 150 because this 150 that get into the bio tower. This 220 get into the primary clarifier. So the primary effluent is primary clarifier. So this kind of statement is a common statement given during our exam. So you must understand well which value that you should use. Either the raw BOD or the effluent coming out from the primary clarifier. So in this case, the influent BOD is 150. So this is LE, the BOD effluent, not 10, because 10 is not achievable at the moment. The current effluent milligram per liter. This is the recirculation flow. The recirculation flow is 1.5 of the wastewater flow. Actually, it is telling you that this is the R value equal to 1.5. So this is the N, and then this is the K20. So you need to calculate the hydraulic loading, and then the second question is that if we increase the R ratio equal to 2, can we meet the standard of 10 milligram per liter? Okay, so this is given, this is the equation. We have to find QV, right? Okay, we have to find QV. So QV is available in this equation, and the other QV is available in this equation. Here, we, but we don't have A, and we cannot assume A. So the only way to calculate the hydraulic loading is to use this equation. Okay, this equation seems to be quite complex, but it can be simplified. So here we have what is given by the questions: D equal to 6 meter, Li 150, Le 30, R 1.5, and K20, and temperature is 25 degrees Celsius. So just now the question gave us the K value at 20. As you know from your experience with BOD, if the K value is different, if the temperature is different than 20, you have to do the conversion. You have to convert the K at different temperature from K20. So here we have to find K25 from K20 using oh, did I miss the equation? Using this equation. Okay, this equation. In your exam, you will be given so many equations, and you will see different K value conversion equation. So it is very important for you to familiarize which equation is used for which system. Okay, so first we calculate this. Okay, using the equation to convert this. So we have K25 equal to K20, and we get the K25 equal to 0.065 per minute. And then from there, we will calculate QV from this equation. Okay. So we will use this equation, LA equal to LI plus RLE. We do not have, okay, we can solve this, LA, because we have LI 150, this is 1.5, T, this is 1.5, so we will get 78 milligram per liter, that is for LA. So this is LA, this is 78 milligram per liter. LE is equal to 30. Okay, so with this equation, we punch in the number 30, 30, 78, 1 plus R, this is 1.5, minus 1.5. So the problem is with this. Okay, sorry, this equation is 0.065 multiplied by 6. It's not x to the power of 6, yeah? It is 0.065 multiplied by 6. Divide by QV to the power of n, which is 0.44. Okay, again, look at this equation properly. LE 30 given 78, we calculated just now. This is 1.5, this is 1.5, this is the K value. The depth of the diameter, which is 6, this is multiplier, this is not variable. And then this is QV that we want to find, and then to the power of n, which is 0.44. So what you should do now, Okay. Okay, I've already fixed this. Okay, this is how it looks like. I forgot to fix the previous one. Okay, so let's say m equal to this. Let's take this as equal to m. M equal to 0.0065 times 6 divided by QV 0.44. So let's solve for this. So we have this, okay, 30 divided by 78 equal to 0.39. So this is m. So this is exponent to the minus m. So this is 1 plus 1.5, 2.5 minus 1.5 e to the power exponential minus m. Okay, this we keep this m as m. This term as m. So we solve for m. Okay, so we can solve for m and we get m equal to, okay, this is, you bring this to the left. Sorry, you solve for em, put it to the one side, and then you solve for e to the power minus m. Then you solve for m ln of 0.61, so you get 0.4. M is equal to 0.94. Okay, and then this is equal to this value, which is 0.00656 divided by QV. Now, having this only one unknown, you can solve for QV. So your QV is equal to QV to the power of 0.44 equal to 0.789. So you remove the 0.4 right side. So you solve for QV equal to 0.584 meter cube per meter squared per minute. So the answer is in meter cube per meter squared per time. It can be per minute, it can be per hour, it can be per day. But don't put the answer as meter per minute. That is wrong. You should, the unit is not correct. You should put the unit in terms of meter cube per meter squared per time. Whether you want to use per day, per minute, doesn't matter, but it has to be meter cube per meter squared. Any question? Understand? Okay, all right. Then we go to the second question. Check the effluent R squared when R is equal to 2. So now we know this QV. So this QV will be used for the next question because QV is equal to Q divided by A. Okay, QV is equal to Q divided by A. So the A is fixed actually. A and Q is fixed. So this QV will be fixed despite your R value. Whatever R value that you use, Q and A is fixed. So we will use this QV. Next question. So what we will do, okay, now we have this QV which we calculated just now. So the rest are the same. But now our R is equal to 2. Okay, not 1.5, sorry. It is R equal to 2. Let me change this 1 minute so that nobody will get confused. Okay, R equal to 2, but we do not have LE. We want to find LE now. Okay, we want to find LE. The rest are already being filled up with numbers. So what is LA? Okay, so for this LE over LA is equal to 0.343. Okay, this is LE over LA. So LA is equal to LI plus RL. So this is equal to, okay, what we do now, LE over LA equal to 0.343. So LE, this is LA. 1 plus 2 equal to 3. This is 150. This is 2LE. So we can use, looking at this, we can put LE on the left side and the rest on the right side. So you can calculate your LE, which is equal to 22.19 milligram per liter. So just now, our R initially was 5. BOD effluent is 30 milligram per liter. Now we change the R to 2 and we get LE equal to 22.19 milligram per liter, which is still higher than 10 milligram per liter. So the question is now, can we do that? So the answer is that when you change R to 2, you still get unsatisfactory BOD value. So you have to increase your R to much higher value in order for LE less than 10 milligram per liter. But that is not part of the question. Okay, so this is how you do the checking. You have already calculated your QV just now because you do not know your A value, so you have to use all the equation. Okay, you have to use all the equation, and then you put in whatever value in the equation, so you get your LE. Any question? Okay, no question. So if you don't have any question, for those of you who has not punched in, this is the last point of exit for you to punch in. So I hope you have already downloaded your notes and there is question. Okay, before that, sorry. That is trickling filter. Now we go to rotating biological contactor. This is very brief, RBC. Okay, so how does RBC looks like? RBC is also once quite a famous. We have used it at some places, not that famous, but we have used it. But it is no longer being used, only at certain places. In Johor Bahru area, this is still being used at Hospital Sultanah Aminah, okay, HSA, being used over there. But other than that, I've never seen RBC being used. Okay, so what we have here, we have a plate. Okay, this is plate like your CD. Okay, if you see a CD, this is how it looks like. And we have a shaft here, and this will rotate. Will rotate very slowly. Okay, it will rotate very slowly. So if you can see here, this is the influent and so as it rotates, some part, this is the wastewater. So as it rotates, some part of the disc will be soaked in the wastewater or immersed in the wastewater. Some will be exposed to the air. So as it rotates, so some part will be immersed, some part will be exposed, some part will be immersed, some part will be exposed. So when the disc is immersed in the wastewater, that is the time when the food is absorbed by the biofilm. Goes to the air, that is the time when the wastewater, or sorry, the biofilm is exposed to the air, oxygen will get into the biofilm. Okay, and after some time, similar to the trickling filter or biotower, the biofilm will get thicker and thicker, and eventually some of the biofilm or the microorganism will die, and the biofilm will peel off from the disc and get into the bottom of this biofilm, sorry, the reactor, and it will go with the effluent. Oops, sorry. So this is how it rotates slowly. there are many type of media being used for this trickling filter. These in form of corrugated metal, different type. Okay, so this is how it works. So this is the disc. Okay, each disc has its area. The design of it is quite interesting, but we are not going to do that in this class. So this is the motor which will rotate the disc slowly. The disc has to be very light because it is too heavy, then it will be difficult. It will be difficult for the motor to rotate the disc. One of the problem with this trickling filter is that because the shaft here is exposed to the water. Okay, there are many metal parts being exposed to the water. So, and this media, this media, really it will get heavier and heavier. And because of the weight of the media, the shaft can break. Okay, the shaft can break. And you see this corrode. Okay, the corrosion will also cause the motor or the rotator to have problem to rotate. So these are some of the issues, main issues related to this rotating biological contactor, making it not favorable to be used in the market. That it is not that favorable, especially in Malaysia, although some other parts of the world are still using it because of the broken shaft and also because of the corrosion at the metal ball bearing caused by the exposure to the water. Okay, that is some introduction on rotating biological contactor. So this is your assignment this week. Question 2, question 4, due date is 31st of December. Again, send it to me and with this name, HW4, first name and UTM ID. For those of you who has not turned in your homework, please do so. You have up to 5 p.m. today to send your homework. After that, homework will no longer be accepted. And if you can get access to this book, I advise you to read the 376 to 389. It will give you a better information, discussion on trickling filter, biotower, and also rotating biological contactor. Any question?